Good afternoon, everyone. Thank you for joining us today. My name is Andrea Baer, and I'm the Climate Services Program Manager in Western Region, and we have been working on a climate seminar series for you all this year at headquarters and a few of the regions. So we're excited to say this is our first one. And Michelle LaRue is going to talk to us today about what's new with ENSO at the Climate Prediction Center. But first of all, I just want to tell you what's going on for the rest of the year. We've got at least one a month planned, possibly two in June. And so I really want to encourage everyone to join the new VLab Forum for Climate if you haven't already. It's really important you do that in order to get the latest information. So please try and do that if you would like the latest on all of these seminars. But we've got topics such as the MJO, several of the Climate Prediction Center's products like the Global Tropical Hazards and Benefits product, the Week 2 U.S. Hazards Outlook. Next fall, we're going to start up with winter teleconnections. We have a part 1 and part 2. And then we're going to look at the stratosphere and the impacts from that to wintertime teleconnections with the stratosphere. So that'll be like sudden stratospheric warming and polar vortex, things like that. So we've got a few fun things planned. You can always provide suggestions to your Climate Services Program Manager at the region for other topics if you have some good ideas. So without further ado, I will turn things over to Michelle LaRue, who is our ENSO expert at the Climate Prediction Center and someone I personally rely on a lot to get the right information from. So Michelle, what is new with ENSO at CPC?
All right, thanks so much, Andrea. And I want to thank Andrea because we do these little ENSO updates, these telecons, every now and then, and she very astutely observed that there's been a lot of changes in the ENSO product in the last couple months. So she said, hey, I think you should go to the field and present this new work. So I'm very pleased to be able to do this today, and we'll go ahead and kick this off. So there are 3 new items, really. The first one started in November 2020, and that is when we started providing probabilities for ENSO strength. In the past, we've only provided probabilities for the chance of El Nino, the chance of neutral, and the chance of La Nina. So it was only 3 categories we were giving probabilities for. And now, essentially, we provide probabilities for a lot more categories, and I'll talk a little bit more about that and how to interpret what we're doing. And then the second item is the new ONI. So the Oceanic Nino Index is our main time series that measures ENSO variability. It tells us roughly that we're in El Nino or La Nina. And those values are updated. Interestingly, we do that every 5 years. So we have a slightly faster update pace than the rest of our products. In part because there's a lot of climate trends in our sea surface temperatures. If you look at maps of sea surface temperatures, you'll often see a lot of red, which indicates above average temperature. So it's really important when we're monitoring ENSO to focus on the departures from the average. And so the average is constantly changing, it's constantly warming, and so to get that as updated as possible, we've gone to 1991, 2020. And then the third item, which is really, really brand new, in fact, our first peer-reviewed publication was published last month on relative sea surface temperatures. And as I'll explain, this is becoming increasingly important because while the last 30-year base period using 1991, 2020 is fine, and we should be updating those base periods, it actually isn't enough for ENSO monitoring. We actually in real time still kind of lag what's happening in the climate, and that poses a problem for ENSO monitoring, and I'll talk a little bit more about that. So many of you are familiar with this, I'm sure, but just to quickly review, we have an ENSO alert system. And so we're either in El Nino or La Nina watch, which basically means that there's a potential for the development of El Nino, La Nina in the next 6 months. There's an advisory when we're actually in the event, when El Nino, La Nina conditions are observed. And then there's a final advisory after the conditions have ended. Not active, of course, is what it says, neither El Nino, La Nina, or observed. Right now, we just happen to be in a La Nina advisor. We actually update our ENSO forecast next week, next Thursday. So we'll be reevaluating that in the coming week. Again, I know this is a review for some of you, but just in case, one of our key indices or time series that we use to measure El Nino La Nina is the Nino 3.4 region, which is that red dash box you see there in the East Central Equatorial Pacific. It's an important box. There are others, but this particular box is strongly correlated with other aspects of ENSO. You know, changes in the winds and convection. We basically need to see a lot of coupled changes in the ocean and the atmosphere. And so Nino 3.4 sea surface temperatures is kind of a key way to get at that. And so to define El Nino, we want to see thresholds in excess of about 0.5 degrees C or greater, and La Nina less than -0.5 C. And of course, this is relative to the climatology or the base period, which I'll be talking more about. And it's been warming up over time. So again, we need to be subtracting the most recent climatology as possible. And so the Oceanic Nino Index, you may hear this as well. I almost use it interchangeably with Nino 3.4, but the ONI is simply the 3-month running average in the Nino 3.4 index. You can monitor the Nino 3.4 index on daily, weekly timescales as well, but we prefer seasonal because ENSO is fundamentally a seasonal climate phenomenon. And so it's important for us to see changes over the span of the season. And so for this, we rely on the ONI. Okay, so one of our new transitions is this gorgeous table of numbers. Yeah, I think this is actually a really cool product, but our presentation here leaves a lot to be desired. You can access it at that link below. You can also access it from our monthly discussion. At this time, I do have a Python app that would be a lot cooler, and I'll show you that in the coming slide. But NCO still has to purchase certain software and whatever. I won't get into details of that, but this is essentially our stopgap is showing this big table. But the information for strain probabilities is in here if you look closely. Each column is showing, the threshold in Nino 3.4 or the ONI. The rows are showing the target season. So this is the season we're trying to make a forecast for. This is an older table, so it's not current right now, but that top row would be for the October, November, December season. And so the middle two columns there are the thresholds for El Nino greater than -0.5, and then the threshold for La Nina less than -0.5. So we're basically interested in the chance or the probability that it's in excess of those thresholds. And so the numbers in the table are actually percentages. Those are probabilities. And so for example, here is a November, December, January forecast. And here we're saying that there is essentially a 54% chance of Nino 3.4 index or ONI value being less than -0.5. All right, and so a -0.5 is a stronger event. Usually when it's in that category, we're talking about a strong La Nina situation. And we did have that last fall. We were pretty close to getting our strong thresholds. We actually fell short of that. We went to, I think our maximum amplitude was about -1.5. 3 degrees C. So it didn't quite make it there, but that's what you would expect. Essentially, 54% means that 46% of the time you will not reach that threshold. And so anyway, hopefully this gives you an idea that now you can get more information on the intensity of strength of ENSO by looking at the strengths table. This is kind of a mock-up. The actual product won't look like this. This is something I did kind of on the side. And it's a Python app, and essentially what you do is you would go into the window there and you would type in your threshold of interest in the DINA 3.4 region. So in this example, I picked -1.3, and so you plug that in, hit enter, and then you would get a plot that looks like this, which gives you the percent chance exceeding that threshold of -1.3. So in this case, because we're on the negative side of La Nina side, we're talking about being even more negative than -1.3. And so this is the probabilities for all the following seasons in excess of that threshold. And so this is a really nice, powerful tool because you can basically pick your poison. You can pick any threshold you want. If you're interested in only extreme ENSO events, you can, put those larger numbers in, those larger thresholds. You may have users that don't even care about the -0.5 thresholds. You could put in something lower, something closer to 0. So it really allows a lot of flexibility in terms of getting the percent chance of a future outcome. So we're excited about that tool, and hopefully we'll be able to roll out the more flexible Python app in the future and not have to rely on just that table. So some of you may be wondering, and it totally makes sense, well, I don't, while it might be like, interesting that an event's going to be strong or not, why should anyone care? Well, we find, and there's a lot of different ways to look at this, but the stronger the event is, the stronger the forcing is from the tropical Pacific Ocean. So it's generally the case that larger values tend to relate to more significant impacts globally. And this is just one way of looking at this. If you look at the x-axis here, this is the standardized MENA 3.4 values. Values there in the lower left are essentially La Nina events, and values in the upper right are El Nino events. And the y-axis is showing spatial correlation. And so basically I'm taking two maps. One of my maps is the typical El Nino or La Nina impacts map, like what you would expect historically. And then I basically correlate that with the map that is observed for all winters. So here's a concrete example. On the left is a global map of precipitation anomalies for 2017-18 winter. And on the right is the, bottom right there is the typical, La Nina pattern during those winters. And so I'm not going to go through every detail here, but the correspondence there is about, the correlation is about 0.5. And so that essentially means that about 25% of the spatial variances share between these two maps. And so what we find is that the spatial correlations increase the stronger the event is, which is why you see in that scatter plot that kind of tilt from the upper right to the lower left. So essentially we like stronger events in part because they tend to relate better to impacts that we see. It doesn't guarantee that you'll get a specific impact in your region or your local area. There's still a lot of noise, a lot of unpredictable variance that we can't explain with ENSO, but by and large, it does push probabilities in a certain direction, which is why things like intensity tend to be of interest to us. And the other thing is that in recent years, there's been a lot of interest and talk in what we call El Nino flavor. So there's a greater appreciation now that sea surface temperature anomalies they don't look exactly the same from event to event. 1997-98 had a lot of amplitude in the Eastern Pacific. That was a strong El Nino. But a lot of these weaker events tend to have amplitude maybe in other regions of the tropical Pacific. So basically this plot, which comes from this BAMS paper, a review paper on understanding ENSO diversity, I really like it because it gives you an idea for the variety of flavors that you can get with El Nino. The output here is from a long run of the GFDL climate model, but I have also done this in observations, and it more or less it looks a lot like this. The only problem with using observational data is that we don't have a very long record of it, and so you don't see the relations jump out quite as cleanly as you do in this model. But they do follow this kind of rule of thumb, and the rule of thumb is this: is that the maximum amplitude tends to be related to the peak strength and sea surface temperature anomaly in tropical Pacific. So, as I said here on the upper right here, this means essentially the maximum sea surface temperature anomaly is occurring more in the Eastern Pacific. So that longitude, about 240 east, is in the Eastern Pacific. And so those months tend to be strong, and they tend to have this structure that looks very similar to what you see in the bottom right there, which is a canonical event. This is from 1997-98. A lot of people call this now an Eastern Pacific El Nino event because the amplitudes are kind of butting up there right against South America, a lot of warmth all the way to South America. And but I think in recent years there's been more appreciation for the fact that this is a continuum. It's not like these flavors just neatly, they're not perfectly in the Eastern Pacific. You know, they can appear in other regions of the Pacific, and it varies from event to event. So this is 2009-10, and then peak amplitude actually occurs somewhere closer to the date line. But as you can see, the warmth actually stretches pretty far eastward as well. So this event, when you look at it in certain metrics, takes on basically an appearance of a combination of flavors, both Eastern Pacific and also what I call a Central Pacific El Nino, or a lot of people use the term Modoki. And this tends to be this cluster of dots in the lower left there. And as you can see, and from the y-axis, the peak sea surface temperature anomaly is on the weaker side, especially relative to the ones that set up more in the Eastern Pacific. So quite often, the Central Pacific events tend to be weaker in amplitude. Some of you may be interested in dots that I'm not featuring here in the lower right of the scatter plot. Those are interesting cases, and I'm not going to, go into a lot of detail there, but those conventionally are just basically weak warmings off the coast of Peru and Ecuador. They actually are not, those are often not accompanied by a full basin ENSO response, where you have a lot of changes in the tropical convection and the winds. So they tend to be more of what I would call a coastal El Nino flavor. So we don't focus so much on coastal El Ninos. If you're an El Nino, or if you're an El Nino expert in Ecuador and Peru, though, you might be very interested in those. But for the United States, because we rely on these extratropical teleconnections and impacts, we follow more the full basin or fully coupled El Nino structures. So anyway, it's kind of interesting that we now have this tool for El Nino strength, and that tool will also give you some hints on flavor. That is, stronger events tend to be more of an Eastern Pacific flavor, and weaker events tend to be more of a Central Pacific flavor. But a lot of events will end up somewhere in the middle, which is why the flexibility of the tool and be able to pick whatever amplitude you want is kind of nice to have. And so some of you may be pointing out, well, those regions, like for example, Modoki, Nino 3.4 region, is in the East Central Pacific. The maximum amplitude actually lies outside of the Nino 3.4 region. And what's interesting is that the maximum SST anomalies can be located in other places in the tropical Pacific, but that amplitude is also very strongly related to the Nino amplitude in the Nino 3.4 index. So this is showing a plot where the x-axis is the amplitude Nino 3.4 index. I'm focusing here on El Ninos. The y-axis is the amplitude of the maximum sea surface temperature in the equatorial Pacific, so that can be anywhere in the Pacific. And what you see is this nice relationship, and this is using observational data, where basically what emerges is that the El Nino 3.4 index will reflect the maximum SST anomalies, even if it's not inside the El Nino 3.4 index. It can lie somewhere else in the tropical Pacific, but the El Nino 3.4 amplitude will capture that. So in other words, these weaker Central Pacific events tend to be associated with weaker El Nino 3.4 index values, and the stronger Eastern Pacific events tend to be related to stronger El Nino 3.4 index values. So El Nino 3.4 is a very versatile index, even if it's not exactly located, where the hot spots in SST are located. So just keep that in mind, that this strengths tool, what I'm saying is this strengths tool will also give you hints on what kind of flavor, if you're interested in that. Okay, so to roll out strengths tool, we actually had to make a pretty big change with how we were developing our ENSO probabilities. So remember, I told you before that previously we only issued probabilities for El Nino, neutral, and La Nina. So it was just 3 categories. And basically I would go to my forecast team and I would ask them to fill out a table for 9 forecast leads. And I would say, put in probabilities for these 3 categories. And then each forecaster would do that, and I would average them together, and that would give me my final probabilities. Well, one nice aspect, what makes this strengths tool feasible, is the Nino 3.4 index is close to Gaussian. Oh, to back up, I should say, to basically ask the forecasters to provide probabilities for more categories, like 9 categories or 10 categories, would be very hard. Mainly they would mutiny. They probably wouldn't even do a very good job of it, because you do want to kind of keep to a certain distribution when you're producing probabilities. It gets very, very hard for human forecasters to provide probabilistic information for more than like 3 categories. So, but luckily they don't have to. This strengths tool basically acknowledges the fact that the Nino 3.4 index is close to Gaussian. And so now from the forecast team, I don't ask for probabilities, I ask for the ensemble mean Nino 3.4 value, right? We don't actually put that on our website because it's just the ensemble mean. We need to give people an idea of what the distribution is. But essentially, give me the mean value, average those mean values together, and then I develop probabilities by creating a distribution function where essentially I take into account the observed climatological variance and also the skill of particular forecast leads. And I estimate that using the NME, which is a multi-model average. And so combining all that information, I'm able to basically develop probabilities for any number of categories. And this ends up being skillful. I won't go into details of this because I just don't have time, but there's an ENSO blog post on this new method, which you can see there at the bottom. So if you're interested in details, go to that. And basically, we find this new method, and this is predicting 9 categories. So for all those little increments that I showed you on the strengths table. And basically, it's skillful, particularly in the mean. When you look at the mean RPS skill, the top plot, the new method is definitely better than using a method where we just basically use the objective model ensemble. And there's a couple of reasons for that, but I won't get into it. And it doesn't harm us from a median perspective either, that bottom one. So ultimately, this is what we've been doing since November. Check it out. Happy to get feedback on it, and hopefully you can roll out that nice Python app soon. Okay, so this is the recent ONI values. As I said, since we're measuring this Nino 3.4 region and we're interested in departures from average, it is very important for us to know what those averages are. And so over time, when you look at all our data sets, essentially there's a warming trend in our Nino 3.4 region. And so this is showing the seasonal cycle of total sea surface temperatures in Nino 3.4 from January to December. And those solid lines are, you know, smaller sea surface temperature values. Those are older 30-year base periods. And then our 1991, 2021s, they're up on top, and it has a maximum. It's very clearly a lot warmer during the spring and summer. So clearly some shifting as we go forward in time. So anyway, ONI values are corrected historically by their 30-year base period that existed, you know, that essentially is centered. But obviously right now we can't center a 30-year base periods. We can only rely on the previous 30 years because we can't, you know, with precision say what's going to happen for the next 15 years. So we do this sort of incremental adjustment to our ONI in the basically in the effort to keep up with these climate trends. But we kind of run into trouble here at the end, particularly when the climatology starts becoming older. So what we noticed when we did this adjustment to the base period is, you know, and some of you may be familiar with this. This is a chart on CPC website showing basically historical El Nino and La Nina episodes. The blue are the La Ninas, the red are the El Ninos, and we require at least five consecutive overlapping 3-month seasons for it to be defined as an episode. And so people like this table because they can pluck out, you know, all the historical El Ninos and La Ninas and do composites and various bits of analysis to basically get information on what was happening in local area at the time there was an El Nino or La Nina. So basically what you can see here is that in 2019 to 2020, there was an El Nino, at least flagged in this table, essentially OND, NDJ, all the way to FMA. It is now 5 consecutive seasons, and so it lit up as an El Nino episode. Only problem was, and if you were following us at the time, is we never called this an El Nino. We didn't think it was an El Nino. There were a lot of reasons that went into that, but we basically, you know, called this a not active or neutral season. And part of that, actually one of the major reasons for that, was that our atmospheric variables were not responding, not in a consistent or persistent way. And basically this is a problem, because if the atmospheric variables aren't responding well, then, you know, the dynamics for essentially the teleconnections onto the Pacific North America region become much more murky, much less reliable. So no atmospheric response is a bit of a game changer. And so it is very interesting to us that we had such warm sea surface temperatures, but we did not see that corresponding atmospheric response. And at that time, we did have discussions about the trend. We knew the sea surface temperatures were warming up. We knew we were coming at the end of an old base period and we were about to update to a new one. And so we were running these numbers and we realized that, you know, I think in the next climatology period or climatology update, these numbers are going to go away. And lo and behold, sure enough, the ONI values disappeared there. The values themselves are apparent, but they're no longer in red. So they no longer qualify as an El Nino episode. And so the fact that this table previously defined this as an El Nino is a bit of a red flag. It says something about our method to remove the 30-year base period. What it says and what it implies is that it's not keeping pace with the changes we're seeing in the climate, with respect to the tropical Pacific Ocean. And so that brings me to the final new thing, and this is quite new. This paper, which you can access, below there is a link, and that link is open access. So you don't need any special library privileges or anything. Anyone can download it. And basically, it was kind of a hodgepodge thing. This paper was almost like 4 years in the making, but it came out of a lot of discussions with Gert Jan van Oldenburg, who is over in the Netherlands, Harry Hendon, who's over at Bureau of Meteorology in Australia, Tim Stockdale, who's at ECMWF, myself, and then the last several authors are from the Red Cross, Red Crescent. And they were flagging the same issue that we had been flagging, which is that, you know, there's an issue here. It seems like our base period climatology isn't keeping up as well as it should, and we're starting to see these offsets between these ocean and the atmosphere. And so Gert-Jan van Oldenburg and Harry Hendon acknowledged that there's a trend. You can see it very clearly in these plots. This is showing sea surface temperature trends. A lot of red there. Nino 3.4 region is actually not one of the regions with the greatest trend, but it's still red. There's a trend. There's a trend in Nino 3.4. And there isn't really much of a trend in the atmospheric variables. Different ways to look at this, but this is Southern Oscillation Index, and as you can see, the trend is not as pronounced there. So Gert-Jan van Oldenburg and Harry Hendon were talking one day, and they said, you know what, maybe we should take a look at relative sea surface temperatures, and I will define what that is. But relative sea surface temperatures are important in part because we want to get, and I know I've said this before, but I just want to keep emphasizing this. El Nino and La Nina are fundamentally coupled phenomenon. So it's not just changes in the ocean, but it's changes in the atmosphere too. And we need to see all this feedbacks lock in. If we just see changes in the atmosphere or just see changes in the ocean, but one is not seeing the other, that's a problem. And so we really do need to see that full system adjustment. And so keep in mind that even though we emphasize SSTs, we still, #1 priority on the ENSO team is to be aware and really kind of prioritize the coupled ocean atmosphere system. However, we do have this reliance on sea surface temperatures, and it's for good reason. I mean, one is sea surface temperatures don't vary as much from month to month as atmospheric variables do. If you look at winds, if you look at convection, those fluctuate a lot more than sea surface temperatures, and it's not hard to understand why they do. But it makes monitoring challenging because we do want to not, I guess, be a victim to basically a lot of changes and fluctuations from month to month. We want to see the signal emerge from the noise. The other reason we like sea surface temperatures is better predicted. If you look at all the forecast models, and I've done this, sea surface temperatures are definitely better predicted than any sort of atmospheric variable at longer lead times and better skill. The third reason we emphasize SSTs is there's a really long historical record of SSTs. So you don't get that with OLR, you don't get that with convection, you don't get that with winds. Over the tropical Pacific, if you want a long record that extends all the way back to the late 19th century, it's SSTs, it's sea surface temperatures. So if you are interested in ENSO events in the past and how they compare to the future, you need a long record. And so for us, that's ERSST version 5 that NCEI produces. And so, you know, there's a good reason here that we emphasize these SSTs. Now, some of you may wonder, our table, we emphasize 5 consecutive seasonal average ONI values. Why is it 5? Why is it not 4? Why is it not 3? Well, I have to admit, there is not really a great reason for 5, other than apparently, and this is before my time, a lot of scientists went through a historical record and basically said, okay, 5 is roughly what you need in order to see periods where coupling between the ocean and the atmosphere was most evident. So if it just lasts for, you know, 2 consecutive or 3 consecutive periods, you can't, it wasn't quite as associated with the atmospheric coupling as the 5. But the problem, of course, in real time, when you're updating from month to month, is you can't wait 5 consecutive seasons. Like, I would love to be able to look through historical data. It's very obvious within El Nino, La Nina historical data. But when you're in real time seeing this thing emerge, you know, you're not going to wait 5 consecutive seasons because the event could be over by the time you reach 5. So there's a forecast component in real time, and so it makes the entire problem a little more challenging. And so that's one of the reasons we have the ENSO alert system, which is predicated on conditions. We emphasize this on the blog. This is how we come up with El Nino, La Nina. Basically, we want a monthly value that reaches our thresholds. We want to see persistence. We want to see forecasts, model forecasts that indicate it will remain for the next several seasons, if not more. And we also want to see the atmospheres kick too, all right? So even though our table is not explicitly atmospheric, we still look a lot at atmospheric indices, and we want to see those all kind of merge together before we decide there's an El Nino La Nina event. So as you can imagine, it's really awkward when sea surface temperatures look like El Nino and the atmosphere does not. The top two plots, there are two different events. One's 2014-15 winter, one on the top right is 2019-20 winter. And looking at those maps, I mean, if you were just kind of given those, you would say, yeah, I see El Nino. There's a lot of red. There's a lot of above average sea surface temperatures about tropical Pacific. Isn't that an El Nino? And then when you start digging through the data, and I'm just showing one variable here in the bottom, is outgoing long wave radiation or convection. Those brown areas or those oranges are where it's drier than average. And during El Nino, what you want to see is basically wetter than average conditions. You want to see blues or purples there, extending really from about the date line to the East Central Pacific, roughly. And during these two events, we didn't really see that, right? Maybe we saw it for a span of a couple of weeks. Maybe we saw a sub-seasonal time scale, but we didn't see it for seasonal, and we certainly didn't see it for 5 consecutive seasons. So this was a problem, and we decided, you know what, relative oceanic Nino indices or relative SSTs is starting to look pretty attractive. On the top there is our standard oceanic Nino index. On the bottom is the relative one. These time series look pretty similar, and they are, and they should be. Remember, we are trying to filter trends from that top time series. We're using the moving 30-year base period. The problem is when we get to the end, we're using the past 30 years. And so when you look at the end of this time series, that's really where the interesting stuff emerges. For example, 2014-15 winter is defined, still is, as an El Nino in our table. However, if you look at relative oceanic Nino index, what you can see right below there is it's not. And I agree with that. There was no El Nino during that winter. There was some warm SSTs, but it was probably trend, and we really didn't see much of an atmospheric response. 2019-20, and that top plot isn't defined red because this is our newest 1991-2020 Climo. But if you were looking at the older Climo, it would have been defined red. And so what you can see in the relative one is that it squarely defines it neutral. It's much lower amplitude than what you see in the top plot. And then the other interesting thing is these La Ninas down here in the recent record are actually stronger in the relative index than they are in our past 30 years. So that's another indication that trends are playing a role. And one of the reasons that we should probably start looking at the relative index in addition to the ONI. All right, so I want to wrap this up soon, but why do we care about relative SSTs? Well, you know, ultimately it comes down to convection, and we care a lot about where the convection is because that leads to the teleconnections on the Pacific North America region. And so this is a cross section of the equator. Convection on the equator juices up the Hadley cell and ultimately impacts the location through thermal wind balance of the subtropical jet stream. And I'm sorry for all the words here, but you know, basically, once you get above the atmospheric boundary layer, there is very little in the way of temperature gradients. There's all these tropical instability waves. They really quickly smooth out the temperature gradients. This is a function of the fact that there's small Coriolis on the equator. In the extratropics, this doesn't work because there's a lot of Coriolis, but in the tropics, it definitely does. And so this basically means the small Coriolis parameter means that their surface conditions really set the temperature for the free troposphere. And it does that through the modifying deep convection. So the entire tropical basin has a certain temperature that is set by these surface conditions. The tropospheric temperature are really, because it's connected to the average sea surface temperature across the entire tropics, is really very important. Again, this is true in the tropics. It's important for the local instability. So it sets the environmental lapse rates, and it helps determine whether conditions are more or less conducive for rainfall. Relative SSTs is simply taking the average conditions tropical Pacific, and basically we're subtracting that from the Nino 3.4 index. It's one single measure. We also add a little bit of a weighting, because if you do that, you'll lose variance in your index. And so we re-normalize it in order to produce amplitudes that and variance is comparable to the standard ONI. I won't make you do that calculation. You can just go to that website down there and pull the relative ONI value. So if you're curious whether you know, a real-time event is showing much amplitudes in a relative sense, you can go to that website. So those are my 3 new items. And I really do recommend going to the ENSO blog on climate.gov, because we tend to talk a lot about these various considerations. Once a month, we do a little update on what the current situation is for El Nino, La Nina. And then the other posts, and we update 2 posts a month, tends to be on something else. As you can see, that top article there is actually the relative SSTs that I just discussed. So there's a blog post on that. So if I went too fast, which is possible, you can go to that blog post and read it through. We really try to hit topics that are of interest to people. We take suggestions. There's a comment section on our blog. Feel free to drop a comment and we will respond. We do monitor it. And yeah, so check that out. We also have an archive of past articles. We've been doing this now for over 7 years. So we have quite an archive. We don't just cover ENSO, we also cover things like the polar vortex and other climate topics that are of interest to people. So I recommend checking that out. The other nice thing is we have graphics, and if you're giving a presentation to your users, you should feel free to just lift those graphics and use them for your PowerPoints. We're very happy for you to do that, and you can do that obviously without our permission. And then of course we have our standard set of you know, official operational products here, and email lists, and we're on Twitter and Facebook, so you can get notified that way as well. So that really wraps things up, and I guess we have some time for questions, like about 15-20 minutes here.
Yeah, hey, that's so great. Thank you so much, Michelle. This is Jenna Myers. I'm hosting the webinar, and I am going through the questions box. So if anybody has any questions for Michelle, please put them in the questions or chat pane. I don't know what exactly it is on your window, but you can send them and I will monitor them and go through them. But for the meantime, Michelle, we have a couple of questions from Andrea and Ray. So let me get you the specific question first. So why are the older normals used for ENSO events before 2016? What is the significance of 2016? Or sorry, 2006.
Yeah.
Six.
Yeah, no, that's a good question. So what we're doing with, I could go over this with a table, but essentially so older values are being adjusted by their centered 30-year climatology at that time. So they're not using climatology that's present day, because if you think about it, a La Nina event in the 1950s should not be measured against an ocean that is much warmer than exists today. Essentially, the La Nina of the 1950s should be measured by an ocean that is, you know, the 30-year average around 1950. So we center all these climatologies that are older, and then we sequentially every 5 years start adding more years to these past events in order to get their climatology centered. So 2006 to 2010 are now going to be centered with the 1986 to 2015 base period, and will stay that way. So those years will never again change. But in our next climatology update, you'll start seeing some movement on our numbers going back to 2011, because fundamentally we're starting to update those climatologies, so those are centered as well. Obviously in real time we can't center because we don't know what the future 15 years is, so we use the lagging 30 years, but in these older events we can center them. I hope that makes sense.
Okay, yeah, thank you so much. Let's see, the next question is, with NWS proposing to get rid of advisories, how will this affect the ENSO advisories?
Really good question. Actually, Climate Services Division, I know, has been doing a lot of work on this. And I know that there's some examination of this and how we will change our ENSO alert system, but I have not gotten any information at this point on how we will change it. So I would definitely ask that question of Climate Services Division and see where they are with that.
Yeah, that's so I'm in Climate Services branch. That's a Marina. Marina has been working that angle. I know she's been working with Mike Halpert at CPC on kind of the language. I know she presented it. I thought she presented it at CDPW last October. At least some of there was a survey that was put out to try to figure out what the language would be.
Right. I don't think they had settled down on it because so one of the reasons we don't use words like warning when we say El Nino, La Nina is because warning denotes a bad thing, kind of like a thunderstorm warning or a tornado warning. In El Nino, La Nina, sometimes they can actually lead to favorable impacts. So we don't want to use the word warning. But you know, if we're being told to get rid of the word advisory, we need another option. Right. And so I think that's part of the challenge there.
Right. Right. So I know that, yeah, there's ongoing work on that. Okay, a question came in. Have you used the ensembles to make ENSO probabilities using the raw model SSTs instead of forcing the ensemble to follow the same process as the human? NMME calibration. It seems like this handicaps the ensemble significantly. Hold on a second. I have to expand it.
So I have to admit, I would need you to start from the beginning because I just realized that I can't see the question on my chat box. I can see the ones to organizers. So
right. Hold on one second. I had to expand it anyways. Hold on. Why am I not getting the full question here? All right. I'll try this again. Have you used the ensembles to make ENSO probabilities using the raw model SSTs instead of forcing the ensemble to follow the same process as the human? NMME calib. It seems like this handicaps the ensemble significantly since it doesn't suffer the limitations of humans. There you go.
Well, certainly, I mean, you're getting at the question of whether humans are adding something to the forecast, and that's a very important one. It is one that we look at and we take very seriously because obviously if the models are better than us, we should stay out of it. The problem is they're not. So the human is adding value to the model forecast. This is showing this plot in top right. And the top panel is just the objective multi-model. This is actually from the NME model ensemble counting. So this is basically taking the ensemble, binning up all the categories and calculating probabilities from that. And the problem with that is that the probabilities that are produced, and this is a general issue with ENSO models, is they tend to be overconfident. So they provide too high probabilities. This is particularly a problem during the spring when there's prediction barrier. And so what you can see is our new method by taking the human ensemble does better. And it's not surprising to me that it does because ultimately the humans tend to take into account information beyond any individual ensemble. And so this new method is actually providing an improvement over objective model ensembles. The other thing to keep in mind is that model ensembles are created by humans. All right, there's a lot of different ways you combine model ensembles. I spend actually quite a bit of time working on different ways to correct ensembles from model forecasts. And it's up to the human to decide how it's corrected. Do you use ensemble regression? Do you use Bayesian sort of strategy? There are about a bazillion different statistical ways to derive probabilities from model ensembles. There are also a billion different types of model ensembles. The North American multi-model ensemble, there's one that Europeans put together. They're all different. And so fundamentally, one of the reasons humans are involved is because we're the jury. We have all the evidence in front of us, but no one can agree on how to optimally combine it and do it in a way that is most skillful, and then and it stays that way. That's a really hard ask, and so that's ultimately where the humans are trying to add value. But it is important to add value, and we do take that very seriously.
Okay, great. Thanks so much, Michelle. Last question is, let's see, what are the future changes that we could be looking forward to for ENSO products, monitoring, tools, and that sort of thing?
Good question. Yeah, so it's been a busy period. It's not often that I can give you 3 different adjustments in the span of 6 months. So that was definitely a lot of work just to get to that point. So then the question is, what am I doing now? One thing I do spend a lot of time on is the idea of these model corrections and comparing them. You know, is there a strategy to compare and combine ensemble information that is objectively better than another strategy? I haven't found one, but that could be just because I haven't gotten there. And I also could be that the models are pretty good, or they have a lot of shared features that, you know, are hard to improve upon. And so that's kind of an ongoing project of mine. And then the other thing, and why am I blanking now? Oh, yes. You know, we're very interested in trends. So I'm very interested in trends. And in particular, I'm interested now in trends in the model forecasts themselves. There's a lot of work. IPCC shows that a lot of these coupled models tend to warm up. They tend to project a very El Nino-like SST pattern across the tropical Pacific. So far, at least in the last 40 years of doing this, it doesn't seem to be pointed that direction. We're actually seeing a trend that is more toward essentially a La Nina-like gradient, where it's relatively cooler in the Eastern Pacific and relatively warmer in the Western Pacific. And it's something that actually shows up. These sort of biases tend to show up a lot in our seasonal forecast models even. So one of my current projects is sort of looking at that and trying to understand the role of trends in our seasonal forecast model, how it might be affecting the forecasts. So yeah, I mean, and then that's just me. There's a whole team at CPC. There's oceanographers, there's modelers, and they have their own projects and own ideas that they're exploring and investigating. So I would anticipate you will continue to see a lot in terms of ENSO changes in the future. But obviously, we want changes that add value. We don't want to change something for just the sake of changing something. We want to improve our forecast products and our monitoring. So, you know, but you know, part of that is also improving our knowledge. And so a lot of what we do sometimes is knowledge building to the point where we can make an adjustment.
Okay, I don't think I see any other questions. If anyone has any other questions, please put them in the questions box. Otherwise, thank you so much, Michelle, for this today, providing an update on where you guys are at with ENSO. I'm gonna quickly, just let you know, we did record this webinar and we will post it on the Climate Services Seminar Series webpage after this. Give us a few days though, because Jim Z, who processes the videos, he's out right now. Let me share my screen. I'm gonna take back presentership, okay, Michelle?
Oh yeah, I can stop.
And then I am going to, let's see, where did it go? Let's see, screen 2. Hopefully you can see this. Let me get rid of these. Okay, can you guys see my screen?
Yes.
Okay, all right, great, thanks, Ray. So I just wanted to share that what Andrea said at the beginning of the webinar, that we have some upcoming webinars, and we will be sending out email announcements with the registration links through the Climate Listserv that has now been migrated over to VLab, so be sure that you sign up for that. And Andrea, did you have any last minute parting words?
No, thank you everyone for joining us, and hope that we see you guys for the rest of them.
All right, thank you, and thank you to Michelle. Thank you so much again, and I guess we will have I guess no, we won't see you in the future, but I'm sure they'll be hearing from you at some point, and be sure to
Yeah,
check out her ENSO blog.
yes, yes. We'll set up a virtual for now, but yeah, thanks so much for having me for this.
All right, have a great day,
Michelle.
guys.
You too.
Bye.